Hi everyone, I'm Ghislain Vieilledent. I'm an ecologist at CIRAD, which is a French research center based in Montpellier. So I will present you a joint work done with my student Jeanne Clément, who is in the room. And it's about using Rcpp packages for easy and fast Gibbs sampling MCMC from within R. So this is the outline of my presentation. I will first shortly present Rcpp and associated Rcpp packages. Then I will show you how is it possible to use this package to run a small and simple Gibbs sampler. And the third point will be about using these packages in a real case example. And it will deal with joint species distribution models. So I will explain later what is it about. So first, what is Rcpp? It's an R package to extend R with C++ code, and the main advantage is that C++ is fast and it accelerates R. So it was written by Dirk Edelbeutel and Romain François, and it has its own website. So this is a simple Rcpp example. So we have some C++ code, and what you just have to do is to include the Rcpp headers when you want to write a function, and include also a small comment to export your function into your R session. Then you can just use this function using the source CPP function from the Rcpp package. And so this function will both compile and export your function into the R session. And then you can use your homemade addition function to have the result of the addition between two numbers, for example. So this example shows that it is very simple to use Rcpp in C++ code. So what are the main advantages of Rcpp? In fact, it includes functions to compile the C++ code, to export the function in your R session, and you can also interchange R objects between R and C++. And you can easily use Rcpp in R packages using specific functions. So a second Rcpp package is called Rcpp GSL, and it makes the interface between R and GSL. So GSL is the GNU scientific library. It is written in C, and it is for C and C++ programmer. And the main characteristic of this library, the most interesting for Gibbs sampling, is that it includes reliable random number generator algorithms and also thoroughly tested and fast random number distribution. So for example, GSL includes, for the version 2.6, 38 random number distributions, and while the R API includes only 24 random number distribution. And it is really easy to implement a new random number distribution from the GSL-based distribution. For example, in the following example, we have developed our own truncated normal distribution. And usually the random draws are faster with GSL than with R. So for example, for the gamma distribution. So this is an example of Rcpp GSL code. So in your C++ code, you just have to include the Rcpp headers and the GSL headers. And then you can use the GSL functions to randomly sample numbers, for example. So this is the GSL ran Gaussian, for example, in this example. And then you can use your homemade random number distribution, here a normal distribution, in your R session. Then there is also the Rcpp armadillo package. So Armadillo is a C++ library for linear algebra and scientific computing, and it performs efficient matrix operations. And Rcpp Armadillo make the interface between R and Armadillo. So this is an example of a linear model regression fitted thanks to Rcpp Armadillo. So again, you just have to include the headers and write your own function. And you can use it in your R session. One important point is about the licenses of these libraries. So they use free software licenses, such as GNU GPL or APH license 2. So you can modify and redistribute these softwares and reuse them in your own R packages, for example. So now a simple example of Gibbs sampling using Rcpp. So Gibbs sampling is commonly used in statistical inference to estimate parameters of statistical models. And so you start with initial values for the parameters, and then you sample iteratively the parameters following given distributions. And these distributions depend on the previous value of each parameter. And so you repeat the step iteratively to obtain Markov chain Monte Carlo. And the samples approximate the joint distribution of all the variables. And the Gibbs sampling can incorporate more advanced algorithms such as Metropolis hastings, slice sampling, adaptive rejection sampling, or Hamiltonian Monte Carlo. So a Gibbs sampler involves several loops, both at the MCMC level and at the parameter level. You will extensively use random draws and matrix computation in the case of conjugated priors, for example. And so, in this case, Rcpp GSL and Rcpp Armadillo are really useful for efficient Gibbs sampling. I will demonstrate that on a small example. So I will compare the execution time between Rcpp, and Rcpp including Armadillo and GSL on a small Gibbs sampler. So this is the R code for my Gibbs sampler. So as you can see, we are drawing X, and it is a function of Y, and Y is also drawn randomly using a normal distribution and is a function of X. So this is the R code. So we use the R gamma and R norm from R. And this is the C++ code using Rcpp. So here we are only using Rcpp syntax and the R random number distribution available in the R API. So R R gamma and R R norm. And then we compare this with a third approach, including Armadillo and GSL. And here we use the GSL random number distribution. So when we benchmark this, we see that using ARMA and GSL, it's 62 times faster than R and 3 times faster than Rcpp alone. So this is a huge gain of time when you do Gibbs sampling. So now the real case example. So I will present an example of a joint species distribution model, which implements the use of Rcpp and the associated package for the Gibbs sampler. So these models are useful in ecology to fit species distribution models, and they account for species interaction. And they can be used to explain, predict species range, and produce species range map. So the data we use to fit this kind of model, we have species presence absence on each site, and environmental variables describing, for example, the climate or the land cover at each site. This is our statistical model. So we have a random variable called y. So y equals 0 if the species is absent on site I, and 1 if the species is present. So we assume that the random variable follow a Bernoulli distribution with parameter theta, and we can express the probit theta as a linear model. So this linear model includes a site random effect, known environmental variables for each site, also latent variables for site I in the matrix big W, and we have species fixed effect in this model. So the latent variables W, so they are quite important in this model. So they represent missing predictors, and they also represent the main axis of the residual covariation between taxa. So if you want more explanation, I advise you to read the paper by Wharton et al. In 2015 in the journal Trends in Ecology and Evolution, which is describing this kind of model. So the interaction between species is taken into account thanks to the latent variables in big W. So this is a complex model. We have a high dimensionality. We have parameters alpha I for sites, parameters beta and lambda for species. We have a non-Gaussian process. We have latent variables, and we have a mixed model including site random effects. So it is useful for this kind of model to use the hierarchical Bayesian approach. And we have developed a specific R package to fit this kind of model. It is called JSDM for Joint Species Distribution Model. And it is available on CRAN. And we will compare this, our implementation of the model with a second implementation, which is provided by the Boral R package. So Boral is an R package which interface R with JAGS. So JAGS is a common software used for Bayesian inference, and the name means just another Gibbs sampler. And it has been used in the article of Wharton, for example, to explain and describe the joint species distribution models. So we have compared the two approaches and the two implementations using 5 data sets. One is a virtual data set with simulated data, and 4 are real data set with different type of species, so mosquitoes, eucalyptus, frogs, and fungi. So all these data sets have a different number of sites, species, observation, and different number of explicative variables. And you can see that the number of parameters is really huge for this type of model. So we reach, for example, 2,565 parameters for the fungi dataset. And we compare the results between the two implementations of the Gibbs sampler. And we can see that on average, JSDM using Rcpp packages is 4 to 14 times faster than Boral, which is using JAGS. Then we can also compare the root mean square error for the probit theta in the simulated dataset. And we can see that after 30,000 iterations for the MCMC, we reach a much lower RMSE using our approach than compared to using Boral with JAGS. And the deviance is also much lower in our case after 35,000 iterations. So to conclude, I would say that when you have small data sets and simple models, it is better to use R, Bugs, JAGS, or STAN, or INLA, or MCMC GLMM, which already includes pre-built and already available Gibbs sampler. But when you have large datasets or complex hierarchical models, we advise that you build your own Gibbs sampler using R, Rcpp, Rcpp RGSL, and Rcpp Armadillo. And when you know how to do it, the Gibbs sampler can typically be written in about half a day, even for quite complex models such as the one I presented. The advantage is that the code is reusable and easily packageable thanks to Rcpp function. And so we have access to incomparable tools and efficient tools to help us build Gibbs sampler as statisticians. So thank you for your attention. If you have questions, don't hesitate.
Are there any questions?
So differences in speed are one thing, but differences in accuracy of solution are another. Do you have a sense of why your Gibbs sampler worked better than JAGS? And did you compare to Stan?
With Stan? With Stan? With the software Stan? Or? Yeah.
Well, as I said, I think having an advantage in speed
you're right.
is nice and is one thing, but getting a more accurate solution is another thing.
Exactly.
And presumably both you and JAGS are doing Gibbs sampling.
Yeah.
How can you account for the difference in accuracy?
Yeah, in fact, at the moment, I don't explain why our approach is better because the underlying algorithm should be more or less the same. I understand why it is faster, but why it is more accurate, I don't know exactly. The fact is that with the JAGS models, you have to specify, you have a trick, in fact, to specify the latent variable Z that we use due to the probit link function. And so it might be due to that we are converging less quickly with JAGS than with JSDM.
So, and that led to the second part of my question about Stan. Hamiltonian Monte Carlo should explore the posterior distribution more efficiently. So I wondered whether you tried Stan and how that compared.
Yeah, that's a good question, and I think we should also compare to Stan to see how it behaves. So, I mean, in our case, we use conjugated priors. So it should be, I mean, we should reach the convergence quite easily. And, but we should do a comparison also with Stan using the Hamiltonian algorithm.
Thank you. Very interesting.
Thanks.